Okay, so we proceed. So just to recall, so in the last class we have seen if there is a canonical form is given, then we write the standard form, and from there we do the iterations for algebraic form of simplex algorithm. Okay, and we have seen that in order to start this algorithm, what we need? We need one initial basic feasible solution. Okay, and from here, from that initial basic feasible solution, we start at z equals to 0. From there, we have gone to 32, then 34. That was the optimal solution. There is a maximum value was there, and then we have found that x1 was 2 and x2 star was 3. So that was our optimal solution. This is our optimal maximized value. Okay. Z max was there, and we have seen what are the conditions that we have done here. Okay. We have changed. We have thought that why we should take x1 for increment, that the coefficient was maximum, so that it will help us to give the maximum values. Okay. So now we will move forward again, and we have seen then the iteration step. There also we have checked, we have found the values of x1 and x3. We have updated the values, the initial basic feasible solution. It was, so this was second basic feasible solution. Okay, and then this was the third basic feasible solution. Third basic feasible solution, which turns out to be the optimal solution. Okay, optimal solution, which turn. So we can say that we can. I mean, these are the algebraic form, but we want a neat and clean. Actually, within one table, it can say everything. So that is more popular form of a simplex algorithm, which is the tabular form. Tabular form of the simplex algorithm. So, okay, so within this one table, it will tell every story. Okay, instead of writing this one separately one by one, okay, so it does not look compact form. So this is more popular form. This one is actually, yeah, tabular form is the more compact form. It will tell everything that this one, the problem is 1x1 plus 1x2 1x3 0x4 less equals or equal to, after adding the slack variables, equals to, so 3x1 3x2, so 2x2 x3 0x3 and 1x4 equals to 12, and the cost is 8x1 then plus 6x2 plus 0x3, there is a slack variable plus 0x4. So the given problem is actually here, indicated by these numbers. So now, how do we perform these operations? Whatever we have done in this steps, in these 3 iterations, so we will do here also. So for that, just we have to recall the Gauss-Jordan elimination. I hope you have studied, all of you have Gauss-Jordan elimination. So the same thing will be actually happen here. Okay, the first thing, so how to perform these steps? Okay, how do we do this iterations? So that we will discuss one by one. So sometimes we leave out this extra lines to make it simpler form. Okay, sometimes. So this would be the case actually. But we want to make it more, I mean, less number of lines should be there. Okay. So that is our goal. How to perform the iterations within the table. Okay. So for that, there are some basic fundamental theorem actually. This statements are very important, but the proofs are not part of our syllabus. So this says some important theorems. The first theorem says if we have this is actually called a fundamental theorem of linear algebra, sorry, linear programming problems. If the linear programming problem admits of an optimal solution, suppose if it has optimal solution, then this optimal solution coincides with at least one of the basic feasible solution. Remember, when we have discussed the graphical method, there we have seen it can be optimal solution exists, it can be infeasible, it can be unbounded, it can have more than one optimal solution. So all these things are stated by this formula, by this theorem. If it has optimal solution, then this is the optimal solution. Okay, it should be at least one of the basic feasible solutions. So the basic feasible solution is a bigger set than the optimal set. So that's the statement of this. If you want to think about geometrically of this theorem, then it will look like this form. So the theorem, okay, again another theorem says, so let us call 1. If there is a feasible solution to a set of, that is a system of linear equations, m different equations, and n, then a number of variables are unknowns, number of unknowns are n, for which m less than n, and also rank of A is m. Then we have seen that there is a basic feasible solution to the set. That means this guarantees, this is the guarantee of a, if there is a feasible solution to a set of simultaneous equation, then there is a basic feasible solution. So this again from this statement we can see that the set of feasible solution is actually bigger. So this is feasible solution. Set of feasible solutions are bigger than the basic feasible solution. Okay. So that is the main idea of these two theorems. and some corollaries will be there. So this corollary says, if an LPP has a feasible solution, then it has a basic feasible solution. That's what the theorem says actually. If it has a feasible solution, then it will have a basic feasible solution. Okay. Okay. And this is very important. There exists only a finite number of basic feasible solutions to a linear programming problem. Now, if you remember, uh, if these two are feasible solutions, okay, then any combination will be a solution, because if you're thinking about the convex set, so feasible solution can be infinite number of points. It can be infinite. Number of points. Feasible solution can be infinite number of, but basic feasible solution will have only finite number of points. Only finite number of points. Now, do not actually confuse with the basic solution. Basic solution. You remember what is basic solution and what is non-basic solution. So basic solutions are those for which we assume them non-zero, and we assume some of the non-basic as zero, and for them we will solve. But remember, basic solution are not necessarily the feasible solution, because feasible solution means it will satisfy the constraints and non-negativity criteria. For basic solution, we do not use such restrictions that it should satisfy. We are going to solve it a system of linear equation. Then we find whether it is a basic or not, whether it is a basic or not. So, okay. So when this basic solution also satisfies the feasibility constraint, then only we call it a basic feasible solution. That means feasible solution plus basic solution, then it becomes basic feasible solution. Okay. Now we go to the, this is for some reason that this theorems are very important. Now we go to the next topic, today's topic, that is what is the form of tabular form of the simplex algorithm. Okay. Now, if you remember that the coefficients that we are having here, okay, all the coefficients, okay, 3 is there already. So we write it. So x1, x2, x3, x4, and then there are some empty spaces are there. What should be the empty spaces that we will learn eventually. But to start, for starting this algorithm, what we have to decide? We need to find the initial basic feasible solution. Initial. And then we have to verify that who is going to be the next, okay, who is going to enter the basis. So if you just recall, so at this time, initially we had assumed these two are initial basic feasible solution. And then we have seen the next basic feasible solution, we have seen that x1 entered the basis, x1 entered the basis and x3 was already there. Remember, we will change one at a time. For one iteration, we will change only one variable. So this idea will be implemented in the next case also. Okay. So here what we are having, so initial basic feasible solution, so that is, we call it, let us call it xb. Okay. Remember, the set of unknowns can be written as x1, x2. So if you consider about, so basic, sorry, x1, x2, xm, xm plus 1 and xn. So these are the total number of variables xp. So for which we are assuming the basic variable, so we call it basic xp, and others will be called xn, non-basic. Now for here n equals to 4. Okay, and we have two equations and m equals to 2. So m minus n are non-basic. That means so m will be basic variables. So we call it x3 and x4. There is another cost are given, the coefficients. So for x3 the cost is 0. For x4 the cost is also 0. We call it cost of the basic variables. Okay, and the right hand side we have seen this is 5, 12. Okay, this is also called sometimes it is called solution also, because solution will be found in this column. Okay, now what we have to do is, who should enter the basis? Okay. So first we have assumed x3 and x4 are basis, and in the next step we have seen that x1 and x3 was the next basis. Okay. So they form the basis. Then we have to calculate one quantity for which we call it Cj minus Zj. Now Zj is the amount. Let me call it Zj is the, so we find it by this way. Zj is the Zj for this one, 0 into, so Cb into xb actually, Cb times xj. So this can be found as 0 into 1, 0 into 1 plus 0 into 3. Okay, so this becomes 0, and Cj is here, so 8 minus 0, so that becomes 8 minus 0, so 8. Similarly, we calculate 0 into 1, 0 into 1, that is 0, plus 0 into 2, 0, and 6 minus 0, that is 6. Similarly, 0 into 1, 0, 0 into 0, 0, so 0 minus 0, again 0. So 0 into 0, 0, 0 into 1, that is 0. So 0 minus 0, again 0. Okay. Now, in order to calculate this, in order to do this step, we must realize we have to find one identity matrix. So this is the identity matrix here. we should find one identity matrix in the table. Okay. And then the right hand side should be non-negative. So this is 5 greater equals to 0. This is also greater equals to 0. So only then we can start this algorithm. Okay. So both of them are non-negative. Suppose this one was -5. So we cannot start the algorithm. For simplex, we cannot do this. Okay. So let us calculate how do we decide that x1 should be the next basis and x3 will be there and x1 will enter here. In place of x4, we will get x1. So how do we decide that? Okay. So for this first iteration, what we can calculate? We can write one more step actually. So this is let me just okay. Let us first calculate the ZJ value. ZJ value is 0 into 1, 0, 0 into 3, 0. Okay. For starting this basis, for starting this algorithm, we must ensure that these two are satisfied. So first thing, we have found one identity matrix. And remember, corresponding to x3, because we are, suppose this was supposed to be like in this way. For some case, if we get 0, 1, 0 and 0, 1, this is x3, this is x4. Then the identity matrix, for forming this identity matrix, we will have to write x3, x4 should come first and then x3. Then only we will get the identity matrix. In order to get, we have to exchange the position. So x3. So order is very important here. The ordering. Okay. So 1, 0, 0, 1. So that is why we must identify one identity matrix, and the right hand side are greater or equals to 0. Okay. Now we calculate this is 0. Again, this is also 0, 0, 0, and 0. Now Cj is here. So Cj minus Zj is 8. This is 6. This is 0, 0. Okay, that's it. And the Z value that we calculate, Z value is also 0 here. Z is, this is calculated as the cost of the present basis element. This is 0 into 5 plus this 0 into 12. So we are at 0. If you remember the previous step, that is also we have seen. Now the task is to identify how this x1 is going to enter the basis. So find maximum Cj minus Zj. Find the value of maximum Cj minus Zj. So here we can get 8 is the maximum. So for this we will call this would be the entering the basis. So here C1 minus Z1 is maximum. So x1 enters the basis. The question is, who should leave? Who should leave the basis? That is decided by this minimum theta rule. So what is the minimum theta rule? So how do we calculate the theta value? So theta is actually calculated by this way. So once we identify the once we have identified this entering variable, that is, this will be called pivot column. Okay, we will look into this pivot column and we will calculate the theta as, so 5 by 1. These are the elements, and we will divide the right hand side by this and divide the row wise. So this is 5. 12 by 3, so this is 4. The variable that is going to leave this basis is the one which have the minimum theta. So x4, this indicates x4 leaves the basis. As of now, you do not confuse with the basic solution and the basis. There are two things. So basis is actually from the vector space idea. So I think you know this idea. Otherwise, I will tell you the basis of a vector space. So from this idea, we actually get the basic solution. Okay. We do not have the detail of this. This is the core idea actually. But we have these ideas. These ideas are actually supposed to be preliminary for starting this course. So now that we have identified the pivot column, we have identified this is pivot, we call it pivot row. Now we have to find out on pivot element, the intersection between the pivot row and the pivot column. So if you look at this in this direction, so they have the intersection here. So we call it pivot element. So this is our pivot element. Now we have to forward, because we are not at the, we have not reached the optimum. So for that we have to go further. So how to go? Okay. So if you remember the Gauss-Jordan elimination methods, we have to rewrite the new pivot row by dividing every element in the row. Okay. That means, suppose here what we are getting, the second row, this is the second row, this is the first row. We have to rewrite it by dividing the pivot element. Okay. So that means R2 new will be R2 divided by R2 old divided by the pivot element is here, it is 3. Okay. And then the non-pivot row, here it is first row. Okay. First row, what we have to do is we have to modify it. We have to update the solution. So for this new pivot Aij will be old Aij times the, that is the Aij 1 into this. So this will be explained through the example. Okay. So remember we had, so pivot row is this one. Yeah. We had the pivot row. We have entered with x1, x1 has entered the basis, and x4 has left the basis. Okay. So what we do is the new pivot row will be the we will divide the pivot row by 3, the pivot element. That is the task. So if we divide it, so you will get here 1, then 2 by 3, then 0 by 3, 0, then 1 by 3, 0. Sorry, 1 by 3 is 1 by 3. Then 12 by 3, that is 4. Okay. How about this new? So that was our R1, R2 new. We have done R2 old divided by 3. What is R1? R1 new. What we have to do is we have to R1 old. We have to take the help of this one, R2 new, so that, okay. Now, why do we, one more thing we have to identify, because x3 is first and then x1 is there. So the identity matrix should be like x3, x1. So that means 1, 0, 0, 1 we should get in this basis. Okay. So that means we want 0 here and 1 here. So for that, what we have to do? So if you multiply, so okay, with 1, because we have to use this one. This row we are going to use now. This row. So 1 minus 1, that is 0. Then 1 minus 2 by 3, that becomes, so that means R1 old minus R2 new. Okay. So 1 minus 2 by 3, that is 1 minus 2 by 3. So 1 by 3. And then 1 is there. Then 1 minus 0. 1 minus 0 is 1. Then 0 minus 1 by 3. Minus 1 by 3. So 5 minus 4, that is 1. Okay. So we have calculated the second iteration. Okay. Now what are the things? Again, we verify whether Cj minus Zj is actually whether we have reached the optimality or not. The optimality criteria is all Cj minus Zj should be less equals to 0. Okay. So now we calculate whether we have reached the optimal solution or not. So for that, again, we have to calculate the Cj minus Zj. So 8 into 1, that is 8. 0 into 0, so 0. 8 minus 8, 0. So 0 into 1 by 3, 0. 8 into 2 by 3, that is 16 by 3. So 6 minus 16 by 3, 6 minus 16 by 3. So that is 18 minus 16 by 3, that is 2 by 3. Okay, then 0 into 1, 0. 8 into 0, 0. So 0 minus 0 is 0. Then 0 into minus 1 by 3 is 0. Then 8 by 3, 8 into 1 by 3, that is 8 by 3. So we sum up them plus. So 0 into 0 minus 8 by 3, that becomes minus 8 by 3. So if you try to calculate the z value, z equals to here 0 into 1, 0, 0 into 1 plus 8 into 4, 8 into 4. So this is 32. So if you remember this step, So in the second iteration, we have got this one, but that is not optimal solution because all the Cj minus Zj are not non-negative, non-positive. There is one positive entry is there. So this will enter the basis. Okay. Similarly, we calculate the theta. So how do we calculate? So 1 by 1 by 3. This is 1 divided by 1 by 3. So this becomes 3. And then 4 by 2 by 3. 4 divided by 2 by 3. So this becomes 6. So where is minimum? Here it is minimum. Now this is the pivot row. This is our pivot column. So we calculate the pivot element. So we repeat this process in the next step and get the, now what will come? Now x2 is entering the basis and x3 leaves the basis. Okay. So here it is. X1 was already there. Now x2 has come here. Okay. So what we have to do is the cost are now, this is 6, this is 8. Basic cost are now 6 and 8. So here we will get, because we are having this one, so we have to work on the row 1 first now. Okay. So what we do is we will divide this row by 1 by 3. This row is divided by 1 by 3. Okay. So if we do that, what we will get? Sorry, this one was 1. So 1, 4, 0, 1 by 3, 1 minus 1 by 3. Minus 1 by 3. This is 1, 4. Okay. And 3 was the theta value. Okay, fine. So we have to divide. So if we divide 0 by 1 by 3, so this is 0. 1 by 3 by 1 by 3, this is 1. 1 by 1 by 3, so this is 3. So minus 1 by 3 divided by 1 by 3, so this is minus 1. So 1 by 1 by 3, so this is 3. Now we have to R2 new, this one will be new. So R2, old R2 minus 2 by 3 into this new one, new R1. Okay. So for this we will get 0 in, okay. Also since x2 is x2 and x1 are basis, then x2 and x1 they will form the basis. That means 1 0 0 1 will be the basis. So that means we want 1 here, we want 0 here. For that we have to do the subtraction, multiplication. Okay. So for that what we have to do is 2 by 3 minus this. So this will leave. Okay. So this is here. Now we want this to. So from here, so 1 into, sorry, we multiply 2 by 3 and subtract from here. So 1 minus 0, that is 1. So 2 by 3 minus 1 into 2 by 3, so that is 0. And then 0 minus, so this is 0 minus 3 into 2 by 3, so that means, so this becomes minus 2. Then 1 by 3 minus 1 by 3 minus of this one. This is minus of 1 into 2 by 3. This becomes 1 by 3 plus 2 by 3. So this becomes 1. This is 1. Okay. And then 6, not 6, this is theta value. So 4 minus, okay, so this is 3. 3 into 2 by 3. So this becomes 2. 4 minus 2 is 2. So this is 2. Okay. Now whether we have reached the optimal solution, that we have to find out. Again, we calculate the Cj minus Zj value. So 6 into 0, 0, 8 into 1, 1, 8. So 8 minus 8, that is 0. Similarly, 6 into 1, 6, 8 into 0, that is 0. So 6 minus 6, this is also 0. Similarly, this one is 6 into 3, this is 18. And then 8 into minus 2, 16. So this plus is actually 2. So 18 minus 16. So plus 2. So 0 minus 2. So this is minus 2. Similarly, 6 into minus 1 is minus 6. 8 into 1 is 8. So 8 minus 6, that is okay. So 2 again. So here also minus 2. And this would be 6 into 3. This is 18. 6, 2 into 8, that is 16. So this becomes 34. So you get this is the second BFS, basic feasible solution. This is the optimal, because you can see that all the Cj minus Zj are less equals to 0. So this implies there is no entering variable. So optimality reached. If for suppose this one, okay, since these are basic, so they will always be 0. Suppose in some different case, if we get 1 here, then this will enter. Okay. Now, if you look at some observation, when x2 and x1 are basic, their Cj minus Zj is 0. Whether it is true for other iterations? Yes. X3 and x1 are basic, so this is 0, and here it is also 0. If you go to the first iteration, also it will have x3 and x4 are 0, so they are the basic level. So these are the explanation for this table. But when you know all these things, okay, you can just do the calculation on rough edge and you can get the solution here. Yeah. So this will look like simple. And this is the observation, very important. This says the increment, how much we get the increment in the next iteration. Also, if you go from top to bottom, then you look at this value. Initially we had 0, then we had 32, then we had 34. That's the optimal. Suppose from 0 we get 32. In some, if you get instead of 32, again if you instead of 34, if you get 30, that means you are doing any mistake, because this will be increasing if you go from top to bottom. That is the main characteristic of this simplex method, that it will give us increasing and increasing solution, provided we are considering one maximization problem. For minimization problem, it will decrease, if you think. But that maximum minimization problem can also be treated as a maximization problem by some suitable exchanges. Okay. So this says the amount of increment, how much it is increased, that is decided by this theta value and Cj minus Zj value. Okay. So for the first iteration, we had seen that theta is 4 and the Cj minus Zj was 8. And that much amount is actually increased. So if you multiply this Cj minus Zj and this theta value, then this much amount will be increased to the next iteration. So in the second iteration, the objective value becomes 32. Similarly, if you think about this value Cj minus Zj, the entering variable in the second iteration, and the theta value at the second iteration 3, the minimum theta value. So if you multiply them to 3 into 2 by 3 into 3, that is 2, and you will get the increment is 32 plus 2, that is 34. So here it is 32 was in the previous step, and this is the increment. So 0 was the previous step, and this is the increment. So this is also some important observation of this simplex table. Okay. Now, if we just quickly go to the second example. So first, this is canonical form. This is standard form. So what we do is x1, x2, x3, and x4. This is the right hand side. So the cost are Cj. This is 3, 4, 0, 0, xb. Let us see who is the xb. This is basic cost. So if we write it 1, 1, 1, 0. So 2, 1, 0, 1. Here 450. This is 600. Okay. I'll take another 10 minutes. Please wait. I have to explain this by today. Otherwise, it will be discontinuous. So we can get one basis identity matrix. That is the first task we have found. So x3 is there and x4 is here. And both of them are greater or equals to 0. So we can start the process. So the cost are 0, 0. So we have to calculate Cj minus Zj. What will be the value? Cj minus Zj. So this is, since these are basic, so we can directly put 0, 0. Now we have to calculate 3 minus 1. Sorry, 3 minus 0. This is 0. No, this is 3. 3 minus 0 is 3. 4 minus 0 is 4. So this is the maximum. So this will enter the basis. And we have to find out the minimum theta. Then this is pivot column. So column has 1 and 1. So 450 by 1. This is 450. And this is 600 by 1. So this is 600. So minimum is this one. So this will depart the basis. And from the pivot column and pivot row, this is the intersection. Okay. So 1 is the intersection. So what we do is, in place of x3, now x2 has come. So let us write x2. And x4 will be there because we change one at a time. And the basic cost has now changed to 4. And the basic cost for x4 is 0. Okay. Now what we do? We have to divide R1 new is divided by the pivot row, the pivot element 1. So it will be just same 1, 1, 1, 0, 450. Okay. Now what we have to do? R2 new is supposed to be this R1 R2 old minus, because x2 is in the basis, so we want 0 here, and x4 is also in the basis, so we want 1 here. So how do we do that? So we take the help of this old second row, R2 row, and then we just simply subtract the R2 new. R1 new. The updated row, we have to take the help. Updated row is there. Okay. So 2 minus 1, that is 1. 1 minus 1 is 0. So 0 minus 1 is minus 1. So 1 minus 0. So this is 1. Okay. Now that we have calculated this row, similarly, So 600 minus 450, this is 150. So this is Cj minus Zj. Calculate 4 into 1, 4, and then 0 into 0. So this is negative 3. Sorry, 3 minus 4 is negative 1. So this is basis, so we can put it 0. This is also basis, a basic variable, so we can put 0. So 4 minus 4 into 4, this is minus 4. So all Cj minus Zj less equals to 0. So optimal condition satisfies. Optimality is reached. Okay, there is no more actually entering variable. Okay, so here what we can do, so 450 plus so this is 1800. So if you remember the last class, so optimal solution was this one. But if you remember the analytical trial and error method, how many iterations we have done? We have done 6 iterations. But here within 2 iterations we can get the solution. So the objective value was 0, and immediately we can get the optimal solution. So this reduces our effort, time. Okay, so that's how this is better than the other methods. Okay, okay, so that is for simple examples. Now the question is whether if you consider that 0 variables, okay, instead of this negative, if we have 0 here also, then also optimality is satisfied. But what will happen if a non-basic variable, Cj minus Zj is 0, then what? Then what will happen? Okay. So that we have to discuss. That is a matter of concern that we will discuss in next subsequent lectures. But today we will see some more example. Okay, so if you consider about this example, so we have three equations, sorry, 3 constraints. So we'll have 3 slack variables. Okay, so we write down the stable slack variables. And then we calculate, we write down all this data, try to calculate these values. Initially, this is because we have to identify one identity matrix. We have to find one identity matrix. So here it is 1 0 0 0 1 0 0 0 1. So that is our identity matrix here. Okay. So one at a time we will change only one. So we have to find out who is the maximum Cj minus Zj. So here it is. So this is entering. You can remove this. Okay. So that is our initial basic feasible solution. Okay. This is the right hand side. Sometimes it is called also solution because S1 is 24 now, S2 is 21, and S3 is 9. The solution will be found in this column. Okay. So what we do, we identify this one, and this would be our pivot element because the minimum theta is here. So this will leave the basis. Okay. Some textbook actually indicate that this is the pivot row. Pivot row. So that is why they put the arrow in this direction. But if you write it in this direction, that means it is leaving the basis, and this one is entering the basis. Okay. So in the next iteration, you will do again, try to find out these values. Remember, one at a time. So that is why x2 has entered and s1, the slack 1, has left the basis. Now we have to find out. Again, this is the maximum Cj minus Zj. So this is second feasible solution. Of course, this is also basic solution because this will form a basis also. So we can find now this one. Again, we calculate the theta. So theta, minimum theta is here. So that means S3 will leave the basis and X1 will enter. So in place of S3, X1 has come and X2 and S2 was already there. So from here, we can see that Cj minus Zj are less equals to 0. So third feasible solution, it has actually optimal solution. So you can see that actually this problem has how many variables? 1, 2, 3, 4, 5. So 5 variables are there, but within 3 iterations, we are getting the optimal solution. So naturally, the question remains whether there is a relation between the number of variables and the number of iterations. Okay. The answer will be no. By the number of equations or the number of variables, we cannot decide how many iteration it will take. So just one other example. If we have this much, 3 equations, another example, so it can take 4 iterations also. This is 1, 2, 3, and 4. So four iteration it has taken. Okay. So try to verify these 2 examples. This is for practice problem, and this is the possible solution. Verify. I have written here verify. Okay, I am not telling this is the exact solution, but you should verify whether these are actually solutions or not. So we have seen 2 equations, 3 equations, and here it is 4 equations. Okay, I will stop here today. If you have any doubt, you can ask me. Okay, just a few last few words. The thing is, the main 3 steps of the simplex algorithm, what we have seen, the initialization. How do we initialize? We have to identify one identity matrix. Plus the right hand side greater equals to 0. We will perform the iteration steps as long as we do not reach the all Cj minus Zj are less equals to 0 for a maximization problem. Remember, if it is a minimization problem, okay, then some restriction, then it should be greater equals to 0 if we consider the objective as a minimization. But we should follow at least at one approach, because a minimization can be written as a maximization also. So that is why we follow only one notion. One convention is sufficient to justify our answers. So if this is not satisfied, we perform the iteration. But if termination condition is there, so if this is satisfied and there is no entering variable, when okay, we will perform this as done if at least one is greater than 0. iteration steps. Okay, all Tj minus Zj less equals to 0, then we stop. So these are the three main feature of this simplex algorithm. So try to verify those two examples. Okay. Now it is yeah, this is over today. So if you have any doubt, again